We have analyzed an inductor by itself, and we know how a single inductor will work. Now let's consider combinations of inductors. In particular, let's start with a combination of three inductors connected in series. If these are in series, the current has to go through one, and then it has no pathway to go but to go to the next one, and then the next one. This means that you'll have the same current all the way through this series combination of inductors, but the voltages across each individual inductor may be different depending on the inductances. Thus, we can say that the voltage across the first inductor would depend on the inductance of that first inductor, and the current, the voltage across the second inductor, can be expressed similarly, and the same for the third inductor. We distinguish the voltages V1, V2, and V3 because the voltages may be different, but we don't need to distinguish the currents because we know that in a series combination, all of the currents have to be the same. If we want to replace these three inductors with one single equivalent inductance, then we can say that the total voltage between the beginning and the end here must be the same as the voltage between the beginning and the end there. So this voltage V must be the same as V1 plus V2 plus V3. And so we have this relationship here. But V1, V2, and V3 combined can be written in terms of V1 plus V2 plus V3. The derivative of the current is the same for each because the current is the same for each, so we can factor that term out. And what we can see here is that the sum of these inductances times the derivative of the current is the same as if you had one single inductor, and the voltage across that inductor, V, would be that equivalent inductance times the derivative of the current. So since these two terms are the same, that means that these two terms have to be the same as well, and we've come across an expression for the equivalent inductance for these three inductors in series. We didn't need to have three, we could have had two or four or more. So if we want to generalize for a series of n inductors, the equivalent inductance would be the sum of all of the inductances of all of the inductors in that series combination. Now let's consider a combination of inductors that are in parallel. In this case, the one end of these inductors are connected by wire, and the other end is also connected by wire. So we have the same voltage on one side, the same voltage on the other. So there's the same voltage, but the currents can be different. If we pick arbitrarily the nth inductor, so the first or the second or the third or whichever, the current through that one specific inductor would depend on the inductance of that inductor and the voltage across that inductor. And the voltage across the nth inductor is going to be the same as the voltage across all the others because they're in parallel, they have the same voltage. If I wanted to express the total current flowing into this total system of inductors in parallel, the total current in this series of three inductors would be the current through the first one plus the current through the second plus the current through the third. That would be KCL for this incoming current. And I can express these three currents in terms of what we know the current to be for each inductor. We'd have 1 over L1, the integral of the voltage, plus the initial value for I1, and then we'd have 1 over L2, the integral of the voltage, plus the initial value of I2, etc. We can factor out the integral term because the voltage is the same for all of them. That's the definition of being in parallel. And so when we add up the 1 over the inductance terms times this common voltage integral, and then we have the sum of the currents. Well, we can see here the initial currents through each one of the inductors is going to equal the initial current coming into the circuit. We can also say if we're treating this as one equivalent inductance, the relationship between the current and the voltage would be thus. And so we can see, okay, well, this term here has got to be the initial value of the current flowing to that equivalent inductance. The voltage integral is the same as the voltage integral, and so this term here must equal that term so that these two equations align. And thus we've come up with a expression finding the equivalent inductance for a group of three inductors in parallel. We did our initial calculations looking at three inductors in parallel, but it didn't have to be three. We could expand this calculation for a combination of n inductors, however many we want. 1 over the equivalent inductance is the sum of 1 over the inductances of the inductors that are in parallel. And then we also need the initial value of the current. This is the total current going into the total combination of inductors. And that initial value of the current is simply the sum of all the initial currents for all the initial inductors that we have. The thing to remember from all of this is that the inductors in series just add up. Inductors in parallel add up as reciprocals. That means that inductors combine like resistors. So we know how to combine resistors. Inductors are going to add their inductances in exactly the same way. Now let's consider a combination of capacitors that are connected in series. When they're in series, the same current is going to flow in to the first terminal, and that same current is going to flow through all of the capacitors because there's no other path for that current to take. You're going to have a voltage across each one of these capacitors, and those voltages may be different depending on what capacitances you have. But we have an overall voltage V, is the total voltage across this total combination of capacitors, and we can say that the total voltage here, V, must equal the sum of the voltages across each individual capacitor. So if we know what the current flowing through this series is, we know the voltage across the nth capacitor. We have an equation to solve that. We know that the net voltage is the sum of all the voltages. If we pick just 3 capacitors to look at, the net voltage across all of them would be the sum of the voltages across the 3 individual capacitors. Each one of these voltages can be expressed in terms of the current, and again recall that the current term is constant, is the same to all of them because we have the same current in series. So we can factor out that current integral. The 1 over capacitances end up out front of that integral, and we have the starting voltages. So what we can see here is that the initial voltages across each of the capacitors, all of those together is just the initial value of the overall voltage across the overall combination. That's what we would have here if we had one equivalent capacitance. We would have the same current flowing through that capacitor, and we see that the equivalent capacitance for a single capacitor or this term here have to be the same, so that this equation looking at the capacitors individually and this equation looking at a single equivalent capacitance are the same. And thus we have a relationship between the equivalent capacitance and the capacitances in series. We did our preliminary calculation looking at just 3 capacitors, but really we could use any number. We could use n capacitors. 1 over the equivalent capacitance would be the sum of 1 over each of the capacitances that make up that series combination. Similarly, the initial value of the overall voltage across the entire combination would be the sum of all the initial voltages across each individual capacitor in that distribution. Now we consider a group of n capacitors connected in parallel. We know that the current through the nth capacitor has this relationship here. The nth capacitor has a current IN. We don't have to distinguish the voltage because they're in parallel. They all have the same voltage. And we want to compare this to a single equivalent capacitor that has one single capacitance, but it's going to have the same overall voltage and the same current flowing into it as this group of parallel capacitors. And so with this setup here, for a single capacitor, we have a relationship between the current through that capacitor and the voltage across it and that equivalent capacitance, but we want to find the same relationship looking at this combination of capacitors in parallel. And so we can say that the current flowing in is equal to the current flowing through each one of these individual capacitors, I1, I2 through IN. Each one of these currents depends on the capacitance, and it depends on the rate of change of the voltage. The capacitances are all different, so we have to keep those separate, but the voltages are all the same, so we can factor out that common term and put it off to the side. And so if we can say this is the current going through one equivalent capacitor, this is the current going through this combination of capacitances, and the two are equivalent to one another, that means that the voltages have to be equivalent, and it means that this term has to equal that term as well. And thus we have a expression for the equivalent capacitance of capacitors in parallel. The equivalent capacitance is simply the sum of the capacitors. Note here that the equation for equivalent capacitance in parallel is the same as the equivalent resistance in series. And if you go back and look at the equivalent capacitance in series, you'll find that it's the same as the equivalent resistance in parallel. So these capacitors are combining opposite as resistors. So inductors combine in the same way as resistors. Capacitors have the same two equations, but they're reversed compared to resistors. If we compare and contrast inductors and capacitors, both of them have a primary equation. you see the parallels between the two. One value is equal to the derivative, or is proportional to the derivative of the other one, and the reversed. The derivative of current gives you voltage, derivative of voltage gives you current. These equations are essentially the Ohm's law for inductors and capacitors. If we have one relationship between voltage and current, we can integrate a derivative to find the other relationship between voltage and current, and again notice the parallel between those two. An inductor works as a current produces a magnetic field, and the energy in the inductor is stored in that magnetic field, which is due to that current. The charge that builds up on a capacitor creates an electric field, and the voltage across that capacitor is proportional to the strength of the electric field and the strength of the amount of energy stored in that capacitor. So to understand an inductor, you need to know the initial current. If you know the initial current and how the current's changing, you can figure out how the current's going to be later, what the voltage is going to be later. For a capacitor, you need to know the initial voltage. That tells you about the initial charge on the capacitor. If you know the initial voltage and how the voltage is changing, you can figure out the voltage later in time, the current later in time, etc. If we are in equilibrium, where we are connected to a constant source, a inductor is just a coil of wire, and so if we are at equilibrium, the inductor acts as just a wire. The current is some constant amount, the voltage is zero. A capacitor is opposite. A capacitor acts like an open circuit, so at equilibrium, the current through the capacitor is zero, and the voltage should be some constant value. The continuity comes from how this energy storage device operates. A inductor operates on Faraday's law, which is related to the magnetic field produced inside that inductor. So if you try to change the current, a voltage is induced that holds that current to be continuous, so the current can't change, but the voltage can make a jump. Similarly, the voltage on a capacitor depends on the charge of the capacitor, so if you start adding or subtracting charge from that capacitor, the amount of voltage has to be continuous as well. You can't jump voltage because that would mean you'd have charge appearing or disappearing on the capacitor plates without flowing into it. Power is always voltage times current. We just have different equations relating voltage and current for each one of these. We can integrate these two equations to find the energy stored in either an inductor or capacitor. Again, note the parallels between these two. And notice as well the combining, the rules for combination crisscross each other. These rules are like a resistor, and these rules here are opposite of resistors, but the same general equations, the summing the values or summing the reciprocals, is the same in both cases.